Hello! In this video, we're going to go over some basics or a summary of normal modes and then waves, including the wave equation and some wave basics, some quantities that we define with traveling waves. And then I'll talk about energy and power a little bit. I'm not going to talk about standing waves. I'll save that for maybe the next video with sound waves. But it's certainly relevant here as well. Okay. So, the last video covered oscillations. And so we build on that in chapter 5 of the book by French. So the first thing that we consider is two masses connected together by some springs. So the way you analyze this is, you look at sum of all the forces equals mass times acceleration for m1. So this is just mass times acceleration for mass m1. But it depends on not only the spring on the left, so not only the position x1, but also how much this spring is stretched or compressed. And that depends on the position of block 2. So in other words, this term right here, the second derivative of x1 with respect to time, involves both x1 and x2. So it's not quite as simple as just oscillations with one mass and one position. Right? So the key point here, and it's easy to get lost in the details from the book, but the key insight is that if we change variables, then we can get an equation that looks a lot like what we've seen before. So there's some linear combination of x1 and x2, and we don't know what those numbers are. So, a and b right here. We don't know what those numbers multiplying x1 and x2 are. It'll depend on, how strong this spring is compared to this spring, compared to this spring. So it'll depend on all those spring constants, for example. So we don't know what those coefficients are, but, assuming we knew more about the problem setup, there exists a change in variables such that we get this equation right here. And this we know what to do with. This is the equation for simple harmonic motion that we're used to. So these linear combinations of x1 and x2 give rise to special motions that we call normal modes. And this is the normal mode frequency. So for u, it has its own frequency, and for v, it'll have its own frequency. So maybe one of them is the two springs moving together. So M1 and M2 are both moving to the right, they stop, they both move to the left, and they both move to the right, so they're moving together. That could be one mode. So there's some special linear combination there. And then there's also a mode where they're kind of always going back and forth in opposite directions rather than the same direction. And as you can imagine, this mode where they're moving in opposite directions actually has higher frequency. Like they're bouncing back and forth a lot quicker than in the case where they move together. So U and V would be those two separate modes, and with their own frequency, and those two frequencies are going to be different. So you can describe any motion of the system, which is where x1 and x2 are, where those two masses both are. You can describe any motion of the system as a superposition, as a sum of the two normal modes with their own frequencies. So it's just sort of like a different basis. So rather than using x1 and x2 to describe the motion, it's better to describe the motion using these linear combinations. That's the whole point of this. And they have their own special frequencies. Okay, so that's two masses. So we went from one mass last chapter with oscillations to two masses to infinite number of masses. So the next chapter you're not responsible for in the reading, but we still go over it in the lectures just because it builds up and describes how this equation comes about, the wave equation. So the point here is that you can take a continuous mass, like a string, and split it up into a bunch of point masses, as fine as you want, as small point masses as you want. And in the lectures, we go through some of the algebra here. So I just put ... math. You can show that the acceleration of one of these masses, which is moving basically up-down, is proportional to the curvature right there. So it has to do with like a difference in tension. So, the string is pulling this way on this mass and then this way on this mass. So there's a slight difference, which has to do with the curvature of the string right there. So you get this relationship right here, this differential equation right here. And there are some assumptions that go into deriving this formula. So we're assuming like the small angle approximation. So you'll have to see the lectures for the details here and what exactly we're assuming. But under those assumptions, you get this wave equation. So actually, this differential equation is very common, and it describes a propagating wave. So I copy down the equation right here, and you're going to see this lots over your physics career. This is a really general equation describing any wave. So by wave, we mean so like in the case of a string, it's some shape that's moving over time, and the whole shape is moving over time. So it's kind of keeping its shape as long as there's no what's called dispersion, so it doesn't spread out. Yeah, so all waves, everything that has that form that kind of looks like, so it's a wave is the transportation of energy without the net transport of matter. So in other words, a string is going to be, any one piece is like vibrating up and down, moving up and down in the y direction, but the wave here is traveling in the x direction. So one thing we want you to notice is any particle is moving in the y direction, but the wave is moving in the x direction. It has to do with the curvature of the string in the x direction. So be a little bit careful here already with just the variables here. So we have two derivatives of y, with the vertical direction with respect to x, the horizontal position, and then that's related to two derivatives of that vertical position with respect to time. So any one particle is moving up and down, but there's collective motion. This is the theme that we always come back to in this class. There's collective motion of all of the particles moving together, and that collective motion is moving in the plus or minus x direction, and we call that the wave. So any one particle is not moving to the right or to the left, it's just moving up and down as this wave passes by. But the overall description of everything is called the wave, and it satisfies this equation. So in the process of deriving the wave equation, or seeing that this problem gives rise to the wave equation, we also derive the wave speed in this case. So this v right here in this equation is the speed of the wave, and you can check the dimensions work out. It gives them it's a quantity that has dimensions of length per unit time, or SI units meters per second. In the case of a string, it's this right here. You derive this expression right here. This is the square root of the tension in the string divided by the linear mass density, or mass per unit length of the string. And again, you can check those units work out. Okay, one important property, and this is it's a purely mathematical thing, but it gives rise to a lot of physical consequences. Waves obey superposition. So if you look right here, if you have two solutions to this wave equation, y1 and y2, so both of them separately satisfy this equation with the same wave speed. Knowing that, if you look at the combination y1 plus y2 and you plug it into that equation, you can separate out the second derivative as a linear operator. So you can separate out those two terms, and so this linear combination also satisfies the wave equation with that same wave speed. So here's a couple of the physical consequences already. Waves pass through each other. So if you have a string and you have one wave that's moving to the left and one that's moving to the right, in the time period where they overlap, you can just add the amplitudes on top of each other, and so you get a bigger hump. And then they pass through each other. So then this wave right here is moving. It's over here moving to the left, and then the other one is over here moving to the right. Or what's also kind of interesting is that if you have a hump moving this way and then a negative hump moving this way, they'll actually cancel each other out. So you'll have if everything is if this is odd, if they exactly cancel each other out, you actually have a wave where it looks like nothing is going on, but there's like these tensions that are pulling each other up and down, and so that they really will pass through each other. So in other words, there's a moment where this becomes this, and then it becomes these humps moving right along. So pretty interesting that they seem to just pass through each other and kind of ignore each other. They just the amplitudes just add up as they would. They seem to not interfere with each other. Well, so some people would call that perfect interference. Some people would say, I guess in a non-physics class, you would say they don't interfere with each other, but actually we call this interference. They are interfering with each other, and that will give rise to a lot of important phenomena in optics and in physics 4D. The other physical consequence I wrote down here is the standing waves. So what we're describing here are traveling waves, moving to the in the plus or minus x direction. There are cases where the boundary conditions will force nodes on the wave, and so waves. So if you have like a wall here and a wall here, and you have a string, so maybe you have something like this passing this way, it's going to reach the edge and then bounce back, and then reach this edge and bounce back. So really what you have on the string are waves that are moving to the left and to the right at the same time, superimposed. And so what you get is, so you kind of get a random assortment of chaos. However, there are certain what are called standing waves where it doesn't look quite as chaotic. So I guess the lowest frequency standing wave would look like this. So what I'm saying is that there's a certain frequency, and I suppose we haven't introduced what frequency is yet, so maybe this is premature to talk about this, but this wave a short time later will look like this, and then it will look like this, and then it will look like this, then this, and it just keeps going. Any one particle is just bouncing down and up like this. And really what this is two waves that are moving, waves that are moving left and right superimposed on top of each other. So it doesn't look, when you look at this over time, you just kind of see a string bouncing up and down. It doesn't clearly look like it's moving to the left or to the right. We call this a standing wave. We're going to come back to this actually with sound. So that's why we didn't write down any equations for this, because this will also be relevant when we talk about sound waves. And like I said before, we're using terms that we haven't even defined yet, so we'll hold off on that. So your book introduces it in this chapter, but then also in the sound waves chapter, which will be our next topic, we're going to talk about this a bit more. Okay, so the wave equation is very general. Actually, if you peek down here, any equation, so y as a function of x and t opens up a lot of doors for possible equations that you write down. If an equation has this form, if every time there's the variable x, then you also have t right next to it, adding or subtracting, and it's always in a particular, there's always the same relative coefficient between the two. That's what this means. So every time you see an x in the equation, there's also, or every time there's a kx, there's also a minus omega t next to it. If you have an equation of that form, it satisfies the wave equation. So you might want to try that out. Have just not even knowing the form of the function, just plug this into here and see what you get out of it. You'll see that it actually works out with wave speed. Actually, I should write that right here. So the wave speed is omega over k, which is also equal to lambda times f, the wave speed. Anyway, so this is, any wave has this form. There's a special class of waves. So a lot of waves in nature are of a special form, and that's sinusoidal. This right here. So you're going to be studying E&M waves, the E&M waves from antennae. I guess this isn't until maybe physics 100C would you see this. Maybe more directly from your experience. If you plug something into an outlet, the voltage is sinusoidal. The voltage going to whatever electronic device you plug in, that's sinusoidal. Anyway, A lot of waves in nature are sinusoidal in nature. So we want to better understand these. So like I said before, a wave has the form where, it's every time the x appears, the t appears right next to it. So you have kx plus or minus omega t. And because it's sinusoidal, this is going to appear inside a sine or a cosine. We just chose a cosine, but it could be a sine there. So you could have a cosine and a sine term, or just introduce a phase constant. So any linear combination of sine and cosine is just, you can write it as just a cosine, but with a phase offset. So this thing A is the amplitude. So notice that the cosine, everything inside the cosine, the kx, the omega t, the phi naught, those don't have units. The cosine doesn't introduce any units. The amplitude has whatever units y is. So for the case of waves on strings, this would be in meters. But waves describe more general things than just displacements. So in the case of, like I was saying before, with plugging something into an outlet, it could be voltages. And you'll learn all about that in Physics 4C. So this is the amplitude of a wave. Could have any units, depends on what you're describing with this wave. Then these other parts. So this is a function of x and t. So these parameters k, omega, and phi naught are constants. The k is related to lambda, and this has to do with how the wave varies over space. K is called the wave number. It has units of radians per meter. And it's basically the reciprocal of a lambda, with this extra factor of 2 pi. So lambda is like the distance. So if you're looking at the wave, this is the distance from one peak to another peak. This is lambda, and it's a certain number of meters. It's as if someone took a picture of the wave. It's whatever that distance is. What the wave number is imagine you already have a wave, and someone took up a meter stick, took up 1 meter, and they counted how many radians were in there. So it looks like this is 1, 2, 3 peaks in that 1 meter. So it'd be 6 pi radians per meter. So this wave right here that I just drew looks like it has a wave number of 6 pi radians per meter, which corresponds to lambda is 1/3 of a meter. So once you know k, you know lambda, or vice versa. So k and lambda are the same information, but k makes this equation simpler. So you'll actually get some practice on your homework rewriting this sinusoidal wave in terms of lambda, in terms of f, in terms of t, in terms of all these other variables. So just like k describes the spatial, how the wave varies in space, omega describes how the wave varies in time. Omega is the number, so this graph that I was talking about before, this is like y versus x when you're talking about k. But when you're talking about omega, you're actually looking at y versus t. So now we specify a point on the wave, a certain x value, and that particle, if we're talking about displacements, that particle is moving up and down in the y direction. So this is called a history graph. Y versus t is a history graph. Versus before, when I was talking about taking a picture, that's called a snapshot. That's when you freeze time, right? You take a picture. That's a certain moment in time, and you're looking at y versus x. That's a snapshot. This is a history graph right here. So for a history graph, this is the period. It's how long it takes for one particle to come back to its original position. And then related to period, you have frequency in hertz, cycles per second, or frequency in radians per second, angular frequency. And omega makes this formula simpler. So and once you know k and you know omega, it's related to the wave speed like this. So I want to warn you that actually the wave speed depends on properties of the material, like right here, the tension and the wave number. So what I mean by that is if you increase the frequency of waves, you don't change v, you actually change lambda. So if I double f, lambda decreases by a factor of 2, and I don't change v. So you can't change v by changing one of these two things. It's just whichever one of these two things you change, the other one compensates. And these are the most common formula for wave speed in terms of these two parameters. So omega over k is the phase velocity or phase velocity here. And then we also have something called group velocity, which is d omega over dk. So here it's actually the same thing. So I didn't expand on this in a lot of detail, but the difference between group and phase velocity is interesting. So omega as a function of k is called the dispersion relation. So here, in the case of sinusoidal waves, omega is equal to a constant wave speed times k. So omega is proportional to k. But you have other waves where omega is proportional to k squared or square root of k or something. In which case omega divided by k and derivative of omega with respect to k are not the same thing. Here, if you take the right-hand side and you divide by k, or if you take the right-hand side and you take a derivative with respect to k, you get the same thing. You get the same wave speed. So another fun fact about, or another fact that makes sinusoidal waves relatively simple is that this wave speed, this phase velocity and group velocity are the same thing. But we'll deal with more complicated waves there too. Okay, so one last thing. There's a plus or minus here, and that tells you what direction the wave is moving. Remember, not the direction particles are being displaced, which is the plus or minus y direction, but the direction the actual wave is moving. So here it would be the plus or minus x direction, and if you have a minus right there, if it's kx minus omega t, if the two terms have opposite signs, then the wave is moving in the plus x direction. And if these two have the same sign, the wave is moving in the minus x direction. So be careful that this sign and this sign are opposite. The last thing, the last topic I have here is energy and power. So one key thing is the introduction of this new quantity called intensity, power per unit area. Be careful, this is not amplitude, this is area. This is power over area. I read it right there as well. I suppose we're also gonna get into this. We're gonna talk more about this when we talk about sound waves. But the reason we're introducing it already in this chapter is this fact right here, and that is intensity or power of a wave is proportional to the amplitude squared. So this tells us how much energy is in the wave. Even if you are talking about a wave on a string, or you're just flicking a wave pulse up and down, you have a piece of jump rope, or a piece of rope. You hold it taut, so there's some tension in it, and then you start flicking it up and down. If you double the amplitude, you have to supply 4 times as much energy. Right? That's what this is saying right here. If you double the amplitude, you increase the energy by a factor of 4. The energy per unit time, which is power. And then that power is spread out over some area in general for waves in 3D, and that's called intensity. So we'll talk more about standing waves. We'll talk more about this formula when we talk about sound waves. But we are introducing it right now. Okay, so I think, I think you see that we didn't cover absolutely everything, but you see how it fits into the main picture here. So I hope this helps.